Alrighty, hello everybody, this is Dakota, and for today, I'm going to do something a little bit different. Instead of the normal calculator programming videos that I've done so far, this is going to be a bit of a math nerdy kind of thing, and we'll see how it goes. So the first thing we're going to do is going to start with a compass. I'm sure many of you know how to use a compass. It helps if you have many layers of pages underneath, and that will just help because then you can stick the pointy end of the compass right into it without worrying about marking up your desk. My desk is plastic, and so I'm not too worried about it anyway, but this will give us a good grip. So we'll start out by sticking this right in the middle, stick it in there nicely, and just go ahead and rotate it out so you have a nice sized circle. And then you just grip the top and draw it all the way around. You should have a beautiful circle just like this. I'll hold that up so you can see it just a little bit better. And in fact, as with all of the lines in this, I'm going to go over them with a Sharpie marker just so you can see them better. Keep in mind, this will make them less precise, but actually all of the geometry in this video is solely for purposes of being able to see the math that I'm doing better, and it's not actually key to the math working out at all. So if you don't have a compass, just go ahead and draw the circle freehand. It will turn out just the same either way. So we're going to go ahead and go like this, and now we have a nice circle. Maybe a bit chunky, but you can see it better hopefully. So the next thing I'm going to do is I can still see a point right there, and I'll draw it with the Sharpie, but where the compass actually poked into the paper, and that's the center of my circle. So now, using the edge of this protractor as a straight edge, I'm going to go ahead and draw in a diameter, which is just a line that goes straight through the center of the circle and intersects both sides. I'm going to draw it just like that. Hopefully we can still see our center right there. So we now have a circle with a center and a diameter. And we're going to do one other thing. I am going to measure an arc onto this circle. So the way I'm going to do this is I'm going to put the center right in that circle right there and try to line up the edges of this. Going to try to line up the edges of this with the diameter so that the zero marking is right there. And this is a bit tough with a solid protractor like this. It's much easier if you have a see-through one, but again, the geometry isn't too important with this, so it doesn't really matter. And so now the question is, where am I going to mark it? And so first we're going to go back to the trusty graphing calculator, turn it on, and we'll go to a bit of geometry with polygons, because that's what we're going to be making. So, any polygon has, let's say it's a square. Then we could break that up into 4 interior angles of 90 degrees. That is, if I have a square here, just like this, and there's a center in here, each of those angles going out, just that angle there, is going to be 90 degrees, and so are all of them. And that's very good, because each of those angles, 90, isn't just 90 because it's 90 because it's 360, oops, helps if you can see, 360 divided by the number of sides, 4, and we get 90 degrees. Therefore, I'm going to make a hexagon, which is 6-sided, so we'll do 360 divided by 6, and we'll get 60 degrees. That means I'm going to go here, once again line it up as best I can, and at the 60 degree mark, which is right here, I'm going to make a little mark. And again at 120, which is 60 from there, or as you can see, 60 from the other side. Maybe you can or can't. I will hold it up so you can see that better. On here, that is the 60 mark right there, which is the 120 from the other side, and then all the way over to 60 here, which it says 120 right there. So now we have these little marks, and I'll just go ahead and finish them by going like this, and following that line, lining up the pencil mark right there and the center of the circle. I'll just make a little dash on the outside of the circle, or the circumference. Doing that again with this one, line them up, and make a little dash. Now, instead of having to do this over and over, what I can simply do is copy this arc. So I stick the compass in there, and I got lucky that it happens to be my radius. That may not be the case on yours. In fact, it probably won't be, but that's okay. It doesn't matter exactly what size it is. Just change the size of your compass by turning the little dial in there so that it's the same. Again, if you don't have a compass, that's totally okay. Again, this should be the same as that one, but I'm just going to go ahead and copy that arc again down here from this side and from this side. If you don't have a compass, you don't have a protractor, that's totally okay. Freehand it if you want to follow along, or even just watch the video and try and follow along with the math that I'm doing, and don't even worry about the geometry of it. I'll handle that. So we now have 6 points that are hopefully equidistant around the circumference of the circle. Now, what I can do is I can connect each of these points with a line. And this, if I've done everything right, should make a very nice regular hexagon. Now, for those of you who haven't taken geometry yet, any regular polygon just means that all of the angles and the sides are the same length and all of the angles have the same angle measure. So if I've done this correctly, you'll now start to see this hexagon in here with all of the sides of a nice, simple length that are all the same. We don't know what it is yet, but they're all the same, and all of the angles are the same. In fact, all of the angles should have, well, we'll get to that later. All of these angles will have a 120-degree measure, but that's just not important right now, so we'll get to that in a moment. However, what is important is I'm going to draw one more line from the center over here to this point, just like that. Now what you notice is it creates this nice equilateral triangle right here. That means that all of the sides are the same, all of the angles are the same. In fact, all of the angles are 60 degrees, because all of the angles in a triangle must add up to 180. These are all the same. You do 180 divided by 3, and you get 60. And so, these are all the same and equal to 60. The one we care about is this one. However, I'm not going to mark it yet. I will mark it over here just so that it's out of the way. Now, this one right here is 60 degrees. I'm going to do, or I should say what I'm going to do now, is cut this angle in half. That is, I'm going to draw a line that's perpendicular to this line here and goes right to the center. And again, I'm totally eyeballing it. It's just as accurate as I can get it. That makes this 90 degrees, and if this is 60 and that's 90, that means this one must be 30. Which also makes sense because this whole angle here was 60 and we cut it in half, making 30. Now, this is important, and I'm going to say one other thing now. Each radius of the circle, notice a radius is just any point from the center to the circumference. I'm going to call that little r, just for radius. So, that means that this line is little r, 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 but we don't know what this line is, because notice it doesn't go all the way. Well, luckily, we have something called trig to help us figure that out. So, the way this is going to work is that we have this thing called Sohcahtoa, and this means so, ka, these are H's, toa. what this means is that sine, S for sine, is equal to opposite over hypotenuse in a triangle. These are all with right triangles, and I'm sure many of you have seen basic trig before, but for those of you who haven't, I'll go over it now. So if we're talking about this angle, we'll call that angle theta. I ran out of room, so I'll draw it down here. If that angle is theta, then that makes this the hypotenuse, of course, because it's always the hypotenuse. This is the opposite side, and this is the adjacent side. So, for instance, cosine is adjacent over hypotenuse. So, now we'll use that. However, in here, we have actual numbers. So, I'm going to call this side x. And that is not the whole thing. That is just half of this whole line, this little bit right here. Because my end goal for this is finding the perimeter of this whole hexagon. So to do that, I'm going to find half of one side, then double that to find the whole side, and then multiply by 6 to get the whole perimeter. And I'll explain why following here soon. So, we know that this side here is r. That's the hypotenuse. So since we have the hypotenuse and the opposite side, we can use sine to relate them. Therefore, the sine of 30 degrees is equal to the opposite over the hypotenuse, so x over r. Now what I'm going to do here is I'm going to multiply both sides by r, as algebra lets me do, and we get r sine of 30 equals x. Now we know that we need 2 x's to get one side, and we need 6 of those to get the whole perimeter. That means there are 12 x's in one perimeter. That means if I multiply both sides by 12, we now have 12r sine of 30 equals 12x. And we know that 12x is the perimeter. So I'm just going to replace it with p for perimeter. So now, jumping down here where there's more room, we have found that 12r sine of 30 equals our perimeter. Now, the question is, what do we want the perimeter to be? Well, what is the circumference of this circle? The circumference of any circle is 2 pi r. That equals the circumference. So, in this case, we know r, so we can say that the circumference is equal to 2 pi r. And pi, I'm sure you all know this, but again, if you don't, pi is just a constant number that relates the radius and the circumference of every single circle out there. And it's approximately equal to 3.1 for 159265358979323. But that's all that I have memorized. There are many people who know way more than that. So, what I'm going to say though is that this hexagon, the perimeter of it should be pretty close to the circumference of the circle. I know it's going to be low. It's less than that because it's not these rounding edges, it's just a shortcut. But it should be pretty close. So I'm going to say that P and C are equal to each other. Therefore 12r sine of 30 is going to be equal to 2 pi r. Now what I'm going to do here is divide everything by 2r, and we get that 6, because 12 divided by 2 is 6. The r's cancel out, so 6 sine of 30 equals pi, because the 2r cancels out on this side. So now we're going to jump over to the graphing calculator and type in 6, and we need to make sure we're in degree mode. So you go mode over to degree, which we are. So 6 sine of 30 degrees, and it equals 3. Now, 3 is kind of close to pi. Here's pi. We were 0.14159 and on and on and on off. But that wasn't too bad. But what if we had more sides? What if it wasn't a hexagon? What if it was a septagon or an octagon? Or what if it was a dodecagon? Or a hendecagon? Or an icosagon? Or a 96gon? Well, here's what I'm going to do. I'm going to generalize these formulas here so that it doesn't matter how many sides there are. In fact, we can pick how many sides there are instead of at the beginning, at the end. We'll see where that leads us. So, setting this off to the side, we'll pretend we still have that circle, but now we don't know how many sides there are to this shape inside of here, this polygon. So we're just going to call the number of sides n. Now, that means that one of these angles we said was 360 divided by 6, because there were 6 sides. That makes this 360 divided by n, because it's no matter how many sides there are. And then we took half of that to make this little triangle here. And so, that means this angle, this 30, is 360 divided by 2n. So I'm going to write that here. Now, what we did was we said that the sine of that angle, remember this is degrees, so this whole thing is an angle. We said that the sine of that was equal to x over r. We did that somewhere here. Right here. And then we multiplied by r, and so we got r sine of the angle equals x. So what I'm going to do is r sine of our new angle, which is 360 over 2n, or if you simplify, 180 over n, equals x. And then we multiplied x by 2, so I'll multiply everything by 2. And then we multiplied by the number of sides, which was in this case 6. But here I'll just multiply everything by n. And that's still lowercase n, because it's the same one there. So we now have, remember I'm multiplying this on both sides, 2nr sine of 180 over n, this is all degrees, equals 2nx. Well, 2nx is just the perimeter. X times 2 times the number of sides. So this will become the perimeter right there. Now, this is going to be really cool, because once again, just as we did down here, I'm going to set this equal to 2 pi r. So 2nr sine of 180 over n equals, and this, remember, we're saying as n gets bigger and bigger and bigger, as there are more and more sides, this should get closer and closer to the circumference, because then our sides will look like this, and they will be very close. So, this will be the circumference, which is 2 pi r. Now again, we will divide by 2r. That cancels out this 2r and this 2r, leaving us with n sine of 180 over n equals pi. And this, remember, back here, the bigger n was, the better it was, and eventually, if we had sort of infinite sides of this polygon, we would be exactly the circumference. So this will say as n approaches or gets closer and closer to infinity. So let's try it. Let's go. Remember, this is what we want. We'll pick a number. We'll say 9999 sine of 180 divided by 9999 and parentheses. And we can see that we get 3.1415926, but then it differs from pi. So that just means 9,999 isn't close enough to infinity. So we'll try, well, an extra 9 and make it 99,000. So 99999 sine of 180 divided by 99999. And now we can see that we have 3.141592653, but the next number is supposed to be a 5, which would round this up to a 4 as it did in pi. However, this still isn't accurate enough. But you can see that we're getting closer. So if I take some crazy big number, like we'll do 99999999, that's 8 nines, sine of 180 divided by 99999999, we get, at least to the accuracy we can see on the calculator screen, exactly pi. And that is what I was hoping to show you. Now, this is really cool, but some of you might be saying, okay, but are you sure? Like, polygons inside circles getting bigger and bigger with more sides gets pi? But why? Well, let's skip to a new page and let's try something else. So, anytime that I see sine, which is what we were using, I'll write our equation back here at the top. This is n, although that could be any variable. It's just important that it's the number of sides. Sine of 180 degrees over n gets us pi. Now, an important thing to note is that the 180 degrees actually is pi in radians. Radians are sort of another way of measuring angles that are used in trig, and essentially the conversion factor is you take your number of degrees, in this case, well, 180, and you multiply it by pi over 180. That's the conversion factor, to keep it as simple as possible. Well, in this case, those drop out and we're left with just pi. So really our formula could be n sine of pi over n equals pi. Now that's kind of weird. Remember, this is as n approaches infinity. But what if I take that and I divide out the n from both sides? Well, now we have sine of pi over n equals pi over n. That's really weird. Normally if I take the sine of something, like if I take the sine of 90, as you can see on here, it's 1. If I take the sine of 45, it's root 2 over 2, which is approximately 0.707. So it's kind of weird for this sine of pi over n to equal pi over n. Keep in mind, this is as n is getting infinitely bigger. So let's take a step back. What if it wasn't pi? In this case, it happened to be pi because it was 180. But what if this wasn't pi? What if this was just some number y? So this leaves us with the sine of y, and I'm going to make the n an x, equals y over x. Now, sine has this inverse function, inverse sine or arcsine, which essentially, if you try and do the arcsine of sine, you just get the original angle. So I'm going to do the arcsine to both sides, just like this. And it's denoted by to the negative 1 power to get you inverse. So that means that on this side, the arcsine cancels with the sine. We're left with y over x. But on this side, we're left with arcsine of y over x. So this is cool. This means, what arcsine means, if we take sine, that means this right here is an angle, like an angle on a triangle. Say that's 30. And we're taking the sine of it to find the ratio of the opposite and the hypotenuse. But no, now we're taking arcsine, which means we know the ratio of the opposite and the hypotenuse, and we want the angle. Right? So, now over to here. We have a triangle. And this triangle, we know that the angle in here, well, first of all, we know that the opposite over the hypotenuse is y over x. That means that the opposite has to be y, and the hypotenuse has to be x. Okay? And this, we should keep in mind, over here, was still as x approaches infinity, because x is just the new n. So that's important to keep in mind. But we know that if we take, right here, if we take the arcsine of those ratios, we'll get the angle is y over x. So that means that this angle right here is, in fact, y over x. Well, let's look at what this means. This is as x approaches infinity. Well, infinity is kind of hard to wrap our brains around, but what about just as x gets really, really big? So, first thing that we would notice is if this hypotenuse here is getting really, really, really big, that would also mean that this bottom side would have to get really big as well. And at a certain point when x does equal infinity, that is, if, it's like we're programming again, x equals infinity, then it would seem that this value here, we'll call it z would also equal infinity, because we couldn't have this being infinite and this being seemingly finite. So they must both be infinity. Wow. That causes more problems. But maybe not. Because if these are both infinity, then imagine that this point right here is not here, but instead is way out that way, farther than I could possibly hope to see. It is infinitely long. In that case, what is this ratio of opposite over hypotenuse? Well, it's opposite, which is some finite length, so it doesn't matter what it is, whether it's pi or, say, 1, over something infinite. Now, if we think about 1 over 1, that's 1. 1 over 2 is 1/2. 1 over 3 is 1/3. And you'll notice that if we look at the decimal approximations of these, they get closer and closer to 0. These numbers get smaller and smaller and smaller because we're breaking a finite 1 up into many, many, many parts, and more parts all the time. So maybe, as we go along, when we finally get to 1 over infinity, this would equal 0. So then, the sign of the opposite over the hypotenuse would have to equal 0, which seems strange. But remember, sine can equal 0. The sign at 0 is 0. I can prove that to you. The sign at 0 is in fact 0. Now let's take a look at the angle. This is again y over x. This is again x approaching infinity, so eventually we have y, whatever it is, over infinity, which means that's 0. Which means that we have the sine of 0, which is in fact 0. That means that if we take the sine of this angle, which is 0 degrees, because at a certain point the length of y compared to the length of x and z is so small that our triangle looks like this. There's actually a side y in there. There's actually an angle right there that is equal to y over x. But in the grand scheme of things, this side here, x, and this side here, z, are so big that that angle is 0. We have a line. But then that side there, y, is 0. And so the ratio of 0 over anything, whether it be 10 or 100 or infinity, is 0. And so the sine of 0 does equal 0. And all of this must be true. I'll leave you with that. Thanks for watching.